Hello. In this video, we will be going over double integrals and specifically switching the order of integration. This will be extremely helpful for your multivariable classes as double integrals is an extremely important part of it. And switching the order of integration is important because in some cases, you can't just solve a double integral in the way that it's provided to you, and you have to switch it so that the equation becomes much easier to solve. So we'll start by doing two examples where I just switch the order of integration, and then we'll do two more examples where I actually solve the integral. So the first problem is, okay, so here's the first problem, which is 0 to 4, 0 to x, fxy dy dx. And as you can tell, it's dy dx. And since dx is the outer integral, that means that this integral relates to dx, which means that the range on the x-axis is from 0 to 4, and I'll fill in the rest of it. 0, 1, 2, 3, 4. And then since dy is the inner integral, that means that this inner integral is the one that corresponds to dy, which means that the range on the y-axis, the minimum is at 0 here, and the maximum is at the square root of x. So we get the equation y equals the square root of x. And so we just have to plug in a couple points to get this graph looking right. So obviously it'd be at 0, 0, and then you have a point at 1, 1, and a point at 4, 2, which is just about here. And then we can sketch this out. And since it's from 0 to x, that means that the area you have to find is in between those two lines. So the area we need to find is this area right here that ends at 4. And so now you may be asking, how do we switch the order of integration? First of all, we're going to redraw the same graph again that we have drawn. 1, 2, 3, 4. 1, 2. We're going to draw the same graph, except this time we're going to do it so that it's dx dy, where the y variable is on the outer integral and the x variable is on the inner integral. So first of all, we need to determine the range of the y values. So we see that the lowest the y possibly goes is at 0, and the highest the y value goes is at 2. So this outer integral is from 0 to 2. And then the inner integral, which is related to dx, is the range of the x values. So we see that the highest x value possible is here at 4, so that's our max. And then the minimum is along this curve here, which was the square root of x, but now we need to flip the equation to put it in terms of y. So if we have y equals the square root of x, now we need to flip it to be that x equals y squared. And that's achievable by just squaring this whole equation. So x equals y squared, so that means the minimum on this integral is actually y squared. So that is an example of how to switch the order of integration. We went from this one, which is type 1. Type 1 is when you have dy dx, and then we were able to switch the order of integration here to become type 2, which is dx dy. The way you can picture the difference between these two types is that type 1, its lines are vertical, up and down, because your base is the x-axis, but in type 2, your lines are going to be horizontal with respect to the y-axis. So it'll look like that. So that is the first example, and now we're going to move on to the next one. Okay, so here's our second example. It is from 1 to 2, and then from 0 to ln x, f of xy, dy dx. And since we immediately see this dy dx, we can tell that it is type 1, which means that the x-axis is the base axis. So again, let's just draw a basic graph of what this would look like. So since this outer dx corresponds with this outer integral, we know that the range of the x values is from 1 to 2. So I say 0, 1, 2, so it'll be in between 1 and 2. And then the y variable corresponds to the range from 0 to ln x. So that means the minimum is here at 0, and the maximum is at ln x. So it follows the equation y equals ln x. And again, we'll just plug in a couple points to get an understanding of what the graph looks like. So if you have ln of 1, the answer is 0. And then if you have ln 2, the answer is just ln 2. So we'll put ln 2 here on the y-axis, about there. And then the graph looks something like that. And since it's type 1, as we said earlier, that means that the lines are vertical, which means that the area we're trying to find is defined by this inner box here, which is from 1 to 2 on the x-axis and 0 to ln 2 on the y-axis. So that is type 1. And now we need to switch the order of integration. So we're just going to draw another graph. Oh wait, that's not 1. 1, 2, 0, ln 2. So again, we have something that looks like this. And so, okay, this is your x-axis and this is the y-axis. So, in trying to find the double integral for type 2, we must remember that we need to find the horizontal lines, which means that our outer integral needs to be dy. So that means this first outer integral here needs to be in terms of the lowest and the highest y values. So the lowest we can find is at 0, and the highest we can find is at ln 2. So the y values range from 0 to ln 2. And then for the x values, we see that the maximum x value is here at 2. So we can put that in, the max is 2. And then the minimum is along this curve here, which is originally y equals ln x, but we need to switch it to put it in terms of the y variable. So if we do it e to the power of, it becomes e to the power of ln x. This cancels out, so it just becomes x equals e to the power of y. So that means the minimum here is e to the power of y, and that is the double integral. Pretty simple to switch from type 1, which is in terms of dy dx, into type 2 here, which is in terms of dx dy. Again, so type 2, the final answer is from 0 to ln 2 on the y-axis, and then from e to the power of y to 2 on the x-axis. And that is type 2. On to the next problem where we will actually solve the double integral as well. Okay, so here's our next example. We will switch the order of integration and then actually solve the double integral. So again, we're going to start by drawing a graph. We see that it's in type 2 formation. So that means this first integral relates to the y-axis from 0 to 1. And then the x-axis has a maximum at 3 here and a minimum at 3y. So we can picture this as x equals 3y. Or to put in something that's probably easier to understand, we'll just say it's y equals 1/3 x. So that gives us a linear line with a point at 3, 1. So the area is the area between the 1/3 x and this line at 3. And since it's type 2, it means it's horizontal lines. So you might be asking, why can't we just solve the integral as it is now? Well, that is because if you look here, the equation is e to the power of x squared, and that can be hard to integrate with in regards to dx. So what we need to do is switch the order of integration to put it in terms of dy, so that way this whole thing here just becomes a constant. So if we switch the order of integration, we draw a second graph. Real quickly, just like that. Now we're going to be putting it into type 1, where it'll be vertical lines. And so the range on the x-axis is from 0 to 3. And the range on the y-axis is from the maximum is along this slope and the minimum is at 0. And we already found the equation in terms of x. So it is from 0 to 1/3 x. And then we're going to put the base equation. Now it is in terms of dy dx because it's type 1. So now that we have the new double integral, we see that it's much easier to start integrating, so we're just going to start solving it. So this first inner integral is from 0 to 1/3 x e to the x squared dy, which just becomes e to the x squared y, right, because this whole thing here is treated as a constant, to the 1/3 x to 0, which becomes e to the x squared 1/3 x minus e to the x squared 0. This term cancels out, leaving us with 1/3 x e to the x squared. And if we bring that over here, now we can do the second integral, which is from 0 to 3. We're going to plug in the 1/3 x e to the x squared, and now we're going to solve it in terms of dx. See, and now it's much easier to integrate this because you have an x here, so you can correctly integrate this x squared up top. So it'll just become 1/6 e to the x squared. That is the integral of this term, and that is from 3 to 0. So it'll become 1/6 e to the power of 3 squared minus 1/6 e to the 0 squared, which equals 1/6 e to the ninth minus 1/6 times 1, because anything to the power of 0 is 1, which equals 1/6 e to the power of 9 minus 1. And that is the final answer for this double integral. And we see that it was much easier to solve the integral when we switched the order of integration, and it would have been a lot harder to integrate this first term here with dx. I don't know why that just erased. We're going to be moving on to the next and final question. Okay, so in this next integral, we have 0 to 4, square root of x to 2, 1 over y cubed plus 1 dy dx. And so immediately we know we're going to have to switch the order of integration because we see that this term here is going to be very hard to integrate, and it can become much simpler if we just switch the order of integration to have to solve for dx first. So let's first graph it to see what it looks like. We see that dx is on the outside, which means that this relates to the x-axis, so it's from 0 to 4, so 0, 1, 2, 3, 4. And then on the y-axis, the max is at 2, and the minimum is at square root of x, so that becomes y equals square root of x. And we can just graph a simple version of that line. So be one point would be at 1, 1, another point would be at 4, 2. So it would look something like that. And then we also have the maximum, which is at 2. So this is the area of the shape that we're doing the double integral under. And since it's in dy dx, we know that that is type 1, which is vertical lines. And now we need to switch that to be type 2. So if we graph it again from 0 to 4, drawing it a little smaller so I have space here to actually solve the integral. One. We know that it now has to be horizontal lines. It'd be something like, it'd be in dx dy format because now we're doing type 2. And type 2 is respect to the y-axis first, so the range of the y variable is from 0 to 2. And now we need to find the range of the x variable now. So we see that the maximum x value is along this slope here, and the minimum is at 0. So the minimum is at 0, and we know that this slope here is y equals square root x. We need to switch it to put it in terms of y, so it becomes x equals y squared. So we get the double integral is from 0 to 2, 0 to y squared, 1 over y cubed plus 1 dx dy, because now it's in type 2. And solving this will be much easier in dx first, because this y over, or 1 over y cubed plus 1 all just becomes a constant. So Now we can actually start solving the integral. So we'll start with the first one, which is just 0 to y squared 1 over y cubed plus 1 dx, which becomes 1 over y cubed plus 1 x from y squared to 0, right? Because that whole term right here is just a constant. So then becomes y squared over y cubed plus 1 minus 1 over y cubed plus 1 times 0. This cancels out, leaving us just with y squared over y cubed plus 1. If we move this, we can now solve the second integral, which is from 0 to 2 y squared over y cubed plus 1 dy. And now it is much easier to solve this integral under dy because we can just use a u substitution for the denominator, and the y squared in the numerator will be canceled out. So if we just say u equals y cubed plus 1, that means du equals 3y squared dy, or 1/3 du equals y squared dy. And don't forget, we also have to change the range of the integration, so it'll be from 0 to 2, but now it would become from 1 to 9, because you just plug 0 and 2 into this equation here, and you get 1 and 9. So 1/3 1 to 9, 1 over u du, which just equals 1/3 ln u from 9 to 1, which is 1/3 ln 9 minus 1/3 ln 1. ln 1 is always equal to 0 because anything to the power of 0 is equal to 1. So this term cancels out, leaving us with a final answer of 1/3 ln 9. And that is how you solve the double integral by switching the order of integration from a type 1 to a type 2, and then all this math to actually solve the integral, which gives us a final answer of 1/3 ln 9. Thank you so much for watching this video. I hope that it helped you in your multivariable calculus endeavors. Yeah, see you next time. Bye bye.